Thank you, and I'm quite grateful to have this opportunity to share my project with you. Today I'm going to talk on my protein structure compression tool, which is named as Foldcomp. As AlphaFold succeeded in predicting high quality protein structures, we are now having hundreds of millions of protein structures publicly available. The AlphaFold team has published 240 million UniProt protein structures, and it is a 1,100 times increase compared to the PDB database. It actually looks like this, and as you can see at the left bottom, PDB looks like this, and compared to the AlphaFold-DB, it's quite small. And we are facing a never unseen size of structure database. And in not too distant future, we'll have over 100 terabytes of database with over billions of entries. However, dealing huge data is quite painful. It takes time. For example, downloading the whole AlphaFold database takes multiple days. Also, it takes storage and money. This is just for storing, and it takes monthly if you are saving that on the cloud storage. Our team came out with an idea to tackle this problem. We expected that we will have multiple databases of millions of structures, and we are now having AlphaFold database, and also we have ESM metagenomic atlas, which is even bigger than the AFDV with 700 million entries. The problem is current PDB format needs much memory to cope with this kind of database. It takes 23 terabytes for AlphaFold and 15 for compressed ESM atlas. Therefore, we designed a compressed format with 10 times efficient than just saving the floating numbers of atom 3D coordinates. Our idea is to encode the structures using the dihedral angles of the backbone and the side chains. The original atom coordinates can be restored from the encoded dihedral angles, and we used natural extension reference frame algorithm to reconstruct the atoms from angles. During the development of the Foldcomp, we set 3 goals to achieve. First, the compression ratio should be high enough. Second, the loss should be little enough compared to the experimental error. Loss was measured as RMSD between the original and the decompressed structures. And lastly, our Foldcomp should be as fast as possible. And here comes a problem on these goals because it requires more memory to reduce the loss. And during reducing the loss, there was a problem. And our initial plan was just encoding the dihedral angles for the structures, but the problem was that the bond angles are not constant, and the deviations in the bond angles actually lead to the high deviations in the RMSD level. So the bond angles should be encoded to reduce the loss. Therefore, with some experiments, our initial plan was to encode the backbones within 8 bytes, and we could pick an optimal bit combinations to encode both bond angles and torsion angles within 8 bytes with least RMSD. And as you can see here, this is our bit architecture for encoding the backbone angles and the sidechain angles in the Foldcomp. And we uses 8 bytes for backbone encoding and 5 bytes for sidechain encoding. And for the backbone encoding, we use this 5 bits for encoding the residues, which consists of 20 amino acids, and we use 12 bits for encoding torsion angles, except for the omega angles, and 8 bits for encoding bond angles. So that quite reduced the required bytes per residue from about over 90 bytes to 30 bytes. Another problem happens within the reconstruction of the 3D coordinates from the internal angles, and the problem was that the loss accumulated as the peptides gets longer. As you can see here, the left side shows the original coordinates, which is colored as green, and the reconstructed coordinates as the red colored. And we divided the reconstructed coordinates into 6 panels, and as you can see here, the deviations gets higher in later positions. So the solution for this problem was that we conducted the nerf algorithm reconstructions in forward and the reverse way, and we conducted weighted average of coordinates reconstructed from both nerf, and this kind of averaging from both sides reduced RMSD per residue between the original and decomposed structures about 30% from 30% to 40%. Another solution for this loss accumulation problem was that introducing internal anchor points to reset error accumulations. We saved the absolute 3D coordinates for every 25 amino acids, and it reduced quite a lot of RMSD deviations compared to the structures without saving the internal anchor points, and we could reduce the RMS range into 0.1 to 0.2 Armstrong range. And thanks to millimeter detail, Foldcomp was quite accelerated compared to the 2022 ISMB, and it is now as fast as GG. We optimized the memory usage of Foldcomp, and also we found out bottlenecks in the process and fixed it. And this is how the Foldcomp compression works. Foldcomp can read multiple input data types like PDB, CIF, or tar or tar.czips, and it can also read the file list as an input, and it converts the Cartesian coordinates of atom coordinates to anchor the internal coordinates, and it discretizes the angles, and it writes it into the binary FCG format. For the decompression, Foldcomp reads the FCG, and it gets the discretized angles from the FCG file, and it restores the original 3D coordinates with bidirectional nerf and also weighted average, and it writes PDB files from the reconstructed coordinates. We conducted a benchmark with the alpha for the East dataset, and Foldcomp has the best compression rate. As you can see here, the gzipped PDB takes about 70 kilobytes on average, but the Foldcomp binary FCG file takes only 7.7 kilobytes on average, so it's about 10% of gzip, and it takes less than 0.01 seconds for the compressing and the decompressing. So it was almost as fast as gzip in the processing. And the final loss was less than 0.1 Armstrong. And this is the longest proteins in the AlphaFold East dataset. And for saving these structures, it takes about 1.75 megabytes for the PDB files, but for the Foldcomp, it only takes 41.6 kilobytes for saving this structure. So Foldcomp could compress the AlphaFold database into just one hard disk. The raw size of AlphaFold databases was 23 terabytes as mentioned, and it needs HPC to work on it, but we could compress it into 1.1 terabytes and it's available on your workstation. Also, Foldcomp could compress the AlphaFold-DB into just 5 files by applying MM62 database format. And with this data format, we could reduce the unnecessary padding bytes used just like and use the entires, and also it could reduce the overhead from like really many file numbers. So the raw files can be like takes 214 billion files and it can cause overhead in your file systems, but with Foldcomp databases it's just 5 files and it's totally iterable and searchable. And Foldcomp is publicly available as command line interfaces. You can compress with just a simple command like Foldcomp compress some PDB, and the decompression works like Foldcomp decompress other FCZ. Foldcomp supports PDB, CIF, and tar.czip directories, and also text files of file lists. You can download that in the GitHub site. Also, Foldcomp is available as a Python API. You can download it with PIP, and we released the databases, compressed databases of AlphaFold database and ESM Atlas, and also the SweetPros and the model organisms. For the AlphaFold DB, it's just 1.1 terabytes, and ESM it's just 1.8 terabytes. Our lab is actively developing many methods for this protein structure area, and we are having sequence aligner which is named MM62, and also we have structure prediction tool named CollaFold and aligner Fold-SIG, and now we have the structure compressor Foldcomp. And this is our lab, and we are starting a lab at SNU, Seoul National University, Korea, and Millard and Martin actually supported me a lot on this project, and this work is also supported by National Research Fund in Korea and Seoul National University. And thank you for listening.